So in this video we'll introduce heat pump systems for heating buildings. Heat pump system has the exact same components that a refrigeration system has. So if we draw out the system here, we'll have our two heat exchangers, we'll have a compressor, we'll have a throttling valve, so we'll connect these all together. Here we have the evaporator and the condenser here. So in this case, the flow is going in the opposite direction of a refrigeration system. The evaporator is on the outside of the building and the condenser is on the inside of the building. So heat goes into the system at the evaporator, comes out of the system at the condenser to provide heating to the building. Work is input at the compressor. So the coefficient of performance of the heat pump is equal to the heat provided to the inside divided by the work input. Now one thing about the evaporator, since it's outside of the building, frost can build up in the evaporator if the outside temperature is lower than about 2 degrees Celsius and it's a humid atmosphere. So here's a schematic of a heat pump from Energuide, and this is for winter usage. This is a reversible system where the evaporator's on the outside, condenser's on the inside for supplying heat to the building. And you see there's this reversing valve, and we can switch this in the summer to change it to a cooling mode. So all the components here stay the same, and in the summer we switch this valve and we have now an air conditioning system with all the components are the exact same. We just flipped a switch. So the evaporator's on the inside here, the flow's going in the opposite direction, and the condenser's on the outside of the building. So heat's being removed from the building in the air conditioning mode and rejected to outside. Now here's a graph showing the coefficient of performance of a heat pump as a function of the outside temperature. See, as it gets colder and colder outside, the coefficient performance gets much and much lower. So heat pumps are not very well suited for cold climates. The COPs would be very low in a cold climate. This balance point here is where the heating capacity of the heat pump is equal to the heating needed to heat the building. Two types of heat pumps we'll look at are air source and ground source heat pumps. This is an air source heat pump. So on the inside of the building, cold air return goes towards the condenser, it's heated up and supplies heat to the building. There's a little fan there that circulates the air throughout the building. On the outside of the building, air is circulated through the evaporator using a fan as shown here, and that's to draw in heat from the outside. We have that valve, evaporator there, and the condenser's on the inside of the building. So we have air on the outside, which is supplying the heat. Now here's places in Canada where it makes sense to have an air source heat pump. We have this area here, Victoria's there, Vancouver's there, and this has a high seasonal performance factor. So this is where heat pumps are most efficiently used for heating. So it has a high COP. And that's because these have warm climates. This here is a ground source heat pump. And you can see that there's many evaporator coils which are placed underground in this trench dug underground. And you can see that this is quite an expensive system to put in. If we look at a schematic for that, we'll change this around so there's no air, and the evaporator coils now go underground. Consequence of this is the system will work at much lower environmental temperatures, but it's much more expensive to install as well. System's the same, except the evaporator coils are underground at a much higher cost.